So hello and welcome to my thesis defense on the topic RepFair GAN, mitigating representation bias in generative adversarial network. So today I'll be presenting. My name is Kamil Sabah and this work was supervised by Professor Adil Khan. So first we need to talk about the bias problem in GANs. So usually generative models used to have a bias problem. So when they have training data with certain distribution and we train the model on this data, when in testing time we can see that the output or the test doesn't represent the distribution of the training set, even when the training set have equal representation of different groups. And this is what we call the bias problem in the GANs, which we are trying to solve in this thesis defense. So we can more detail on this problem statement and the research objective. So the issue here is how do we measure fairness in GANs? And what causes a GAN to have a bias? Can we train a generator to produce data uniformly? And can we maintain sample quality while implementing fairness? So objective is to define a fairness notation, hypothesize what can generate the bias, test this hypothesis on different data sets in reducing bias, and then to try to keep the quality of the generated images. So first we need to define our notion of fairness. In this case, we will be talking about representational bias. In simplest term, we can say representation bias measure how far from each other groups are in testing data. When we generate the data, we can say. I came up with two examples to make it very clear. So we can say in example 1, we have a GAN which generate images of dogs and cats. If we say images rated for dogs were 45 and for cats were 55%, here we can say representation bias is 10%. In another example, if we have like a GAN which generate images of burgers and pizza, we can say if burgers were 50% and pizza were represented 50%, burgers were 50% and pizza 50%, therefore the bias representation here is 0. So what was the previous work done in this area? So first we can talk about the fair GAN, which from the name you can know it's working on fairness. So fair GAN is an improvement on the architecture of the GAN. Usual GAN have one generator and one discriminator. This discriminator usually, as in all GANs, determine if a given image is synthetically generated or it was a real image. But in fair GAN, they introduce one more discriminator, which can check if an image is from one group or not. So let's say we're generating images of males and females. The first discriminator will say if this image is real or not. The second discriminator will say if it can recognize it's a male or female. And the goal of this discriminator is to achieve statistical parity. So when generating images, we want it to be not distinguishable if it's real or not, and we don't want the second discriminator to know if it's male or female. And by achieving that, the fair GAN authors claim that it will achieve fairness. And there was the Xiu et al. Approach, which worked better even than the fair GAN by introducing one more classifier and one more discriminator to this previous generator. Another method we can introduce in the literature is instance reweighing. So basically what does it mean? It means we give more weights for underrepresented groups and we give less weight to overrepresented groups in attempt to make training process balanced. And there is other methods like post-training, which modifies the distribution in the latent space after training the model. So what is our solution and what does it bring to the table? So our solution is RepFair GAN. And our hypothesis is that there is a correlation between the group distribution and the gradient magnitude for each group during the training time. So here we can see two figures. The one on the bottom shows the gradient magnitude over epochs for training normal and shaded images of the SVHN dataset. As you can see, there's a correlation, obvious correlation between the representation and the magnitude, as the shaded images are more represented in the testing time, and in training time it was having higher gradient magnitude. So based on that hypothesis, we created a training method called group-wise gradient clipping. So how does it different from normal training of the GAN? So in this method, we kind of splitted the data set into two groups. The Let's say in this case normal and shaded, or we can say male and female. And in each batch, we train only from one of these groups, so we can accurately calculate the gradient magnitude for each group during training time. And then we can do gradient clipping for each group. So now we have the hypothesis, we have a training method. We want to test it on several data sets to check if our hypothesis is correct or not. So we used the MNIST dataset, which is 60,000 samples of labeled handwritten digits. And here we created two types of this MNIST dataset. The original one, which have white digits and black background, and the other created dataset, or like version, was black digits and white background. The other dataset we used is SVHN, which is 73,000 images of sample of home street numbers. We also divided into two groups. One of them was the normal images, and the other one was shaded images. We applied a filter to make them shaded. And the final dataset we used was Fairface. Fairface has over 100,000 images of high dimensionality images, like they are like complex images. They have 3 colors, and it's of course more complex than all the other datasets. So experiments and results. For the MNIST dataset, we used the conditional GAN. And in conditional GAN, in this case, we conditioned it on the digits of the MNIST, so from 0 to 9. And then we trained two models, two GANs. One we called it just the CGAN, the normal one, and one is the RepFair CGAN. So the RepFair CGAN uses our training methods. So each training, for each batch we train, we do gradient clipping for each group. And after training these two GANs, we can check their representation when we ask them to generate image digits from 0 to 9. We can see in the CGAN there is a disparity between black background digits and white background digits. But in the RepFair GAN, we can see that this disparity has reduced by a lot. And we can here quickly look at qualitative results. We can see that we did not compromise on the quality, as the images look as good as the normally generated ones. So we move next to the SVHN experiment, and here we used a vanilla GAN. We also used group-wise gradient clipping as our method. But here we didn't just use 50-50% during the training dataset. We didn't have 50% of the images shaded and 50% normal. We implemented and we tested with 20 to 80, we implemented 30 to 70, and 40 to 60. And we noticed that in all of these scenarios, our method was able to, even when the images in the generated dataset were not equal, it was able to equalize them, which we considered as a great win. And here we can see that we didn't compromise on the quality, as the images generated look as good as the original ones. Next, we tested on the Fairface dataset. But in this experiment, we used a vanilla GAN as usual. We used a vanilla GAN, and we also used our training method. But this time, we didn't use group-wise gradient clipping. We just, during the training time, we did normal clipping when we having a normal batch with random images, which can be male or female. Like in this case, we're studying the gender representation. So even without specifying what we are trying to achieve fairness on, without changing anything in the training process, we just added the the gradient clipping by the norm. We noticed that we could have achieved much more fairness, and we can see it was like changed from 34 to 65 to 55 44, which is a huge improvement, even on such complex data set. And for the qualitative results, on the right, we can see the images generated by the FAIR GAN, and on the left, we can see the normal model. And we can see here as well, we didn't compromise on the quality, as they look similar. So in conclusion, we defined a fairness notation for fairness. We defined our fairness notation. We identified a reason for bias in GAN. We created a more fairer training method. and we maintained the quality of the generated images. So what we learned is that there is a positive relation between the gradient magnitude of each group during training time and its representation percentage in testing time. And we learned that by controlling the gradient magnitude using gradient clipping, by the norm, we can reduce this representation bias. I want to give finally acknowledgement to Professor Adil Khan and Patrick Kemfak for their measurable help and their patience and all their support and guidance. Without them, this work couldn't have been created. Much appreciation for them. And that's all from my side. Thank you for your time and thank you for following up with me. Now I am open for any questions. Thank you all.